So we're still in section 2.1, but now we're on page 2, this time talking about rate laws. So the rate law describes the relationship between a reaction's rate and the concentration of reactants. In general, as the concentration of reactants increases, the rate increases. There's a blank there, right? So it increases and it asks why. And so really it should seem pretty intuitive. As concentration increases, there's going to be just more of the reactant, right? But in terms of slightly different idea, reactions are caused when two molecules or two particles collide or come in contact with each other. And so this would say the number of effective collisions result in a reaction rate increase. So the basic idea, you've got more of the reactants, there's more of them, the reaction's going to go faster. That's not the kind of answer that AP really wants to hear. Yeah, there's more reactants, yeah, it's going to go faster. They want to know why. And the why is that you've got just more of these particles around, they're going to hit each other more often, and it's those collisions that's the why. More collisions means a faster reaction rate. If you think back to Unit 1, we had a few where we were drawing like circles, and they were, here's one reactant, here's the other. Something like that. So, first example, and it looks like you've got most of the data, so good. Consider reaction A plus B plus C yields some products. What is this? A plus B plus C yielding products. And we've got a data table here. Data from 4 experiments are shown on the table to the right. The rate law for the reaction was found to be rate equals K, concentration of A to the second power, concentration of B to the first power, concentration of C to the first power. So this is the first you're seeing this concept. This is what's called the rate law. Eventually we'll get to the point where we can figure out the rate law from the data. Right now, it's just given to us. So the rate is dependent on the concentrations. And when we plug in our numbers for each of these 3, along with a K constant, how fast is this reaction going to go? It's going to tell us how fast it goes. So if you look at trial 1, I'm not going to write the entire data table. Trial 1, concentration of A is 0.5, B is 0.3, C is 0.8, and the rate it says is 0.01. You've got that one written down. If we were to put it in here and figure out what's going on, it would give us our numbers. Let's say we were going to look for the rate of trial number 2. This thing right here, the rate. We have a concentration for A, we have a concentration for B, we have a concentration for C. It's all here in the table. What's the problem? Can you see a problem right now? We don't have a K yet. So that's going to be a problem because we're going to have 2 variables, which is not going to be good. But we can figure out K because for trial number 1, we have every single number. So let's use trial number 1 and plug in all of its numbers here. So it has a rate of 0.01. So the first thing that I do is I just went ahead and did all of this, and it came out to 0.0600. Did I agree with you, or are you doing some steps different? Now you'll notice I left the units in here because the units with these are really kind of weird. They get weird quick. And so my units here are molar to the fourth power. We had molar squared times molar, molar to the fourth power. Then I'm going to divide both sides. 0.0600 molar to the fourth power. And so my K value got 0.16. Let's see, everything else went to three snipping figures. Let's say 167. And then our units. They're going to be weird units. So molar over molar to the fourth power, you're dividing, so you subtract the exponents, right? Molar to the negative third times seconds. Very weird units. But I'll tell you this. Every year on the AP exam, there's always a rate loss question.
Isn't the seconds to the negative first?
No, because it was, oh yeah, you're right, sorry. There's always a rate law question, and the first thing it'll say is find the value for K with units. It specifies with units. So you could get the right number, but if your units aren't there, then they're going to mark it wrong. So that's the reason why I carried all these around, because, well, not K. But if you wait until afterwards to try to figure out the units, it's going to be just as painful. Yes, thank you. Seconds to the negative one. So at this point, we have the numbers and we can do trial 2. So let me duplicate this page. This up. All right. So now for trial 2. So now we have the constant and we have 3 concentrations. Now we can figure out the rate of this reaction based on the starting concentrations. So rate equals 0.167 molar to the negative third seconds to the minus 1. Concentration of A, I have 1.50 molar. B is 0.300. C is 0.8. All right, so I got rate equals 0.0902. We rounded our K value. It was 0.1666 repeating. And if you put in a lot more sixes in your calculator, then it would be a lot closer to 0.0900. But that's all rounding stuff. AP would understand. So it's not going to be a huge deal. What's my units for the rate here? Molar per second. So let's go back and look at this. So if you look at, this is going to be molar squared. And so that'll take out two of these and leaves us molar to the -1. Another one takes it out. So we have one capital M left. Molar to the negative seconds, or molar per second. Something like that. Anytime the AP writes something down for you, it's going to look like this. They never do any slashes. They always have -1s on the units. So this is the way it's going to look. They don't care what your answer units are as long as they're right. Either one is okay. Trial 3 and trial 4, we're going to do the same idea here. Did you already do 3 and 4?
Yeah.
You did 3 and 4? Oh, okay.
That would be terrible.
All right. So for trial 3, we're going to set it up in the same way. Rate equals, here's our K, 0.1, and 6666666 repeating. Concentration of A, 1.50 molar. Square that one. Concentration of B is 2.70 molar. Concentration of C is 0.800. And so we put all this in our calculator. The rate for this one should be something around 0.810. Now the units should always be molar per second for the rate. Should be. And a lot of students just kind of assume that the units are here, so they just write it down. And they won't check their units up here. If your units end up wrong, it means that something was wrong with the units up here. So it doesn't hurt to carry them through, but your rate should come out to molar per second. Trial 4, same idea. Here's my same K value with units. And the rate comes out to 0.720 molar per second. So this is the calculation based, and it actually wanted us to explain it without using the direct math. I like to see the numbers first, but let's go back and explain it. So looking at trial 2, we're looking at what changed between trial 1 and trial 2. So I'm going to duplicate this. Yeah. So what happened between trial 1 and trial 2? We're looking at the data table. We want to know what changed. Now, obviously, the rate's going to change. So the rate change, we don't need to really say that out loud. Concentrations. What changed here? So in trial 1 and trial 2, the concentration of A changed. And the concentration tripled. But how did that influence the actual reaction? So we increase this times 3, but look, it's squared. It's actually times 9. And if you look at the reaction rates we have, the reaction rate was 9 times larger. Times 9 reaction rate. So for trial 3, let's compare trial 2 and trial 3. Looking at just these 2 rows, what concentrations are different? So A is both 1.5, C is both 0.8, it's B. Concentration of B changed. The A was the same, the C was the same. This one went up. It's 9 times as much B as in the previous trial. And now compare the rates of trial 2 and trial 3. It was a times 9 reaction rate. For trial 4, if you're looking at trial 4 and you try to compare it to trial 3, they really have nothing in common. But looking at trial 4, if you look back, let's see here, look at trial 2. A doubled 1.5 to 3. C doubled from 0.8 to 1.6. And B stayed the same. So this one, a little more complex. We've got this one, the A times 3, excuse me, times 2. Just right there. So the concentration of A was times 2, the second power. Concentration of C was times 2, but it's to the first power here. So times 4 and times 2. Overall, we saw a times 8 increase, right? Yeah. From 2 to 4, the reaction rate is 8 times the rate of 2. Left. Okay, so we're going to go a little bit further. We might not get all of this page done. You've got the entire data table. You've got all the concentrations. You have all the reaction rates. So here's what we're looking at. The first question says, find the rate law for the reaction. On the kinetics question, or the rate question on the AP exam, this is always part A. It'll say, find the rate law for the equation. You'll see the data table. This is the first question. And here's how it's going to start. This is not your answer, but it's your starting point. You're going to say rate equals K times the concentration of MnO4 minus. We don't know what the exponent is yet. And so you can use X, Y, Z if you want. You can use MNP, doesn't matter. I'm going to put it to the X power, ClO3 minus to the Y power, and H plus to the Z power. So if you look back up the page, we had a rate law in example 1. That's what we want it to look like. Now the X, the Y, and the Z, they might be different numbers, but that's what a rate law should look like. It should say rate equals K, and then whatever follows. So here's how we end up doing this. So let's look for X first. We want to figure out what is the value of this exponent, and we call this the order of MnO4. So X is the order of MnO4. And so here's how we do it. If you're looking at trial 1, everything's 0.1 molar. If you're looking at trial 2, everything's the same except for MnO4. So we can find X. And so here's how we are going to do this. We're going to compare two different reactions at the same time. We're going to compare the rate and everything of 2, and compare the rate and everything of 1. So K, MnO4, this actual number, excuse me. It is 0.25 to the X power, and then we have 1 for ClO3 to the Y power, and this one to the Z power. And these are our 3 numbers from the table. And then for reaction 1, we plug in the numbers for those concentrations. And once you get to this point, we will we'll continue on here. And we also have some actual numbers for rate 1 over rate 2. It was 3.3 times 10 to the negative second, 5.2 times 10 to the minus third. There's a lot of things we can cancel here. For instance, K is on the top and the bottom. They're gone. 0.1 to the Y, 0.1 to the Z. And so we can simplify this. Here we have 0.25 to the X over 0.1 to the X. So if you do 0.25 divided by 0.1, we end up with 2.5 to the x. And then this is, I'll give us the number here, 6.35. So 6.35 is 2.5 to the x. Long bow. All right, so let's wrap this up and then we'll call it. So how do you get x out of the exponent? I remember. Did you have an idea? It's a log. So x log of 2.5 equals log of 6.35. So solving for x, you get something like this, and it ends up. So if you put this in your calculator, you find out that x is 2. And so then we can go back up to the top and where it's to the x power, we can remove that. And from now on, we know that it is to the second power. Continue with this another day.